Playing something which is extremely beautiful. So the goal of this lecture is to discuss the Lagrangian viewpoint toward geodesics, which we showed this morning was equivalent to the length functional being minimized by critical points geodesics. And embed this subject, even as just a special case of something very important, in the Hamiltonian mechanics of the cotangent bundle. And then to start the first steps of symplectic geometry. So I will start here and go there, and then go there. Now, I've given many lectures on this subject, so my lecture notes are probably lying around someplace. But the good formal books which are good in this, including those for the Riemannian part. This book is called Riemannian Geometry, blah blah blah. I don't know exactly the book, but somebody gave it to me here. I think you gave it to me. Thank you. Of course, it's a big book, so you only want to read the first part first. And Arnold, you should always read Arnold if you have the chance. I mentioned this morning. Mathematical methods and mechanics. And that's a little bit here, but very much this transition. And there are many elementary treatments of the last part. So let me call this last part star. For star, I don't know what to suggest, but one possibility is the book of Duza McDuff and Dietmar Salomon. They wrote an elementary book on symplectic geometry, which was published maybe, for me, not so long ago, maybe 20 years ago, something like that. So in fact, he's a friend of mine at ETH Zurich, and one of our students here recently went there and did his master's degree. It's a nice place to do that. Unfortunately, Arnold, I had many projects with Arnold, but he's a little bit older than my generation, and he died too young. He was too young. Maybe died at 70 years old. Maybe he had a stroke. I mean, he rode his bicycle all the time, and one time he simply crashed. And that was the beginning of the end. Probably starting to have some problems. So he's gone. But Joost is director of, also a friend of mine, of Max Planck in Leipzig. You should know that in physics, we have the honor of 3 physics people here. In physics, the tradition in Germany to have Max Planck Institute was very early after the Second World War, maybe even before, I'm not sure. Physicists are very smart with that. Mathematicians are very slow. And the first Max Planck Institute in mathematics was in Bonn, and still is in Bonn, and is coupled also with the graduate school in mathematics in Bonn, which is a very nice coupling. But it is founded by Hirzebruch and such people, and it is very nice. But then Joost and a couple other people founded, he's one of the original directors of the MPE license. This MPE is interested in applied so mathematics and its applications. So Jürgen Joost is a very serious mathematician, for example, but he's also interested in applications. So there's a combined work with physicists. By the way, nowadays with Joost has gone into some biomathematics. It's become very useful to go into bio. But he is a specialist in partial differential equations and differential geometry. And so these, if you take a look at these books, it will help you. Duza McDuff is in Stony Brook in New York, Long Island. And her husband is John Milner, so it's a nice mathematical family. Milner being a very important topologist, but having moved into some form of dynamics. Okay. So we've seen what's going on. Let me review from this morning. We have the length functional of gamma. And this is gamma as a curve from A to B. Smooth curve in the manifold. And this is what you think with respect to the metric, dt. And we showed this morning, of course, the geodesic intuitively, the distance between x and y is the inf of the length of gamma from x to y. Almost always I will consider smooth curves at first, but here you should consider, for obvious reasons, piecewise smooth curves. So this is the distance, and this is given by the length. And it's an elementary theorem that you can easily prove as homework exercise, that this gives a metric a distance function on the manifold. You understand what I mean by that? That means the distance from x to y is equal to the distance from y to x. And triangle inequality, right? And that's trivial. But what you need to check is that if the distance is 0, then x and y are not equal.
So it does not hold for the pseudo-Riemannian case?
What?
For the pseudo-Riemannian case?
I don't know. The pseudo-Riemannian case becomes very delicate. This is Riemannian case, everything here. So this is Riemannian, so let me just re-emphasize this morning, but everything I'm saying now is in the Riemannian case. Okay. And it's a little bit delicate to prove that if the distance is 0, then x equals y, because it's an infimum, right? And of course, the thing is, locally, if here's x, and then you take y out here, and you have some curve, locally, g is approximately the standard metric. Say this is an open neighborhood here, U. You understand what I'm saying? It's a quadratic form, but it has eigenvalues, and the eigenvalues are non-zero because it's a non-degenerate positive definite quadratic form, and the eigenvalues move smoothly with the function. So on a local piece, these things are bounded away from 0. They cannot go to 0 on a local piece because of compactness argument. Okay, so that means that you really have a strong estimate between the standard norm and this norm. And that means that if you leave this guy, which you have to, this piece has to have length somehow estimated by the standard norm, right? Because it's bounded away from below and above by the standard norm. It's more or less the standard norm, not exactly, but bounded away. So that proves that this thing is a metric. This is a distant function on it. Okay, that's a great thing, but I pointed out this morning that L is invariant coordinate by change of the parameterization. That means you can take arc length parameterization can be used. And that means, and this means that it's enough to study something much better, what the physicists told us to study anyway, the action, which here we call the energy. So this is the energy of gamma, or the energy function or curves, or in physics notation, action. And this is the integral of the Lagrangian, which is a function. So gamma, let's say gamma of t is given in coordinates by x1 of t to xn of t. I did this morning. And we'll call this a vector x of t. So I'm looking locally in a coordinate chart now. So, and what we write here is x point, and t dt. So here, in this one, this is a general setting. Lagrangian, which defines an action or an energy. And here, of course, in our case, the Lagrangian is equal to the norm squared. So it's a very simple thing. Very simple. Okay.
So doesn't that mean that in our case the Lagrangian is 1?
What?
So in our case the Lagrangian is 1?
I know what you mean. Because I said it's enough to reduce to arc length. And so the answer is no. So, I understand your point. the solution to, we want to find critical points of of this energy or action. And in fact, the critical points will be parameterized by arc length or some multiple of arc length. So that's good. But when you find critical points, we're going to find them right now. You do work like in high school. You look at f of x plus h minus f of x divided by h. Okay? That's what we're going to do here. So there's going to be some energy thing at some point, plus h, minus the thing at another point, divided by h, and we'll take the derivative. Right? But this movement of h is any curve. So it kills this whole problem, this whole thing with arc length. So we have to now, I've just said, what is the arc length business? The arc length business says that any good curve, any critical curve that we want is going to be almost automatically parameterized by arc length. However, we want to find critical points over all curves. You see what her original question was? Because in some sense the answer to this question is arc length will be 1. Right? Because it will be parameterized by arc length. It's a funny thing, but are you okay on that now? Okay. Okay, so so the idea is to look at this general situation. So all of this discussion here starts with length functional, distance, good enough to think about things with arc length, but when you make calculus of variations, now we're going to do something called calculus of variations. That means we're going to vary, we're doing calculus, but you're varying not a point, x goes to x plus y, we're varying a curve. Gamma goes to gamma plus h. By the way, this is very nicely written in Arnold, and I will try to use Arnold's notation, okay? I just looked it up. Okay. So I will follow Arnold. And he uses another notation, probably the Moscow version of this thing. Phi of gamma equals integral a to b. Oh no, he doesn't use a to b. T0 to T1. Lagrangian of x dot t dt. Is everybody okay with that? All right. So x is now a vector valued function, right? Because we're doing this in a coordinate chart, so I'll write it here to remind you. x1 through xn. Okay. Okay, it's a vector value function, and you want to minimize that. You don't know how to minimize it, as I said this morning, so you take its first derivative and hope that you find a minimum. Don't forget your high school education. That's what you did. You minimize a function, you want to take the first derivative and then check. Okay? That's what we're going to do. So we're going to, the goal is to find critical points, of this action function. Now one thing, if you read Arnold, by the way, he did not have tech in that time, and his translator also did not have tech, but somehow they had a good publishing company, Springer Verlag, and if you have a function, they will write something like this, but in boldface. And when they write that in boldface, I'm just telling you how to read Arnold, because I told you this morning, the first 80 pages of Arnold took me 2 months to read. And one of the reasons was notation. And this means gradient. And of course, what that is completely correct. Right? So it's great, this derivative is the full derivative. It's the derivative of f, but as a not the differential, but just the derivative. So that, if you read Arnold, you will see in boldface, this thing is graded. Okay? Okay. So let us start with Arnold. Let's start with the calculus of variation. As you know, for my lectures here, I try to look up some history. It's very easy nowadays with the web. This first steps in calculus of variations is due to Euler. And this is a very long time ago. It's in the 18th century. And there was this mathematician, here's where I go in the summer. This is Italy, but this part in here is called Piedmonte. And the dialect of Piedmonte, you understand right here is, you know your geometry here, this is Nice, it's very close to you. So France is very close here. And the dialect here, in fact, you know, Italy is a very, very new country. The Italy we know is founded after World War I, basically. So it's a very new country, and it had many regions. So where I go here, I speak German, and where people here speak dialect, it's more or less some form of French. And there was a person here who was named Lagrange, I'll probably misspell it, Lagrange, something like this, maybe G-J, I don't know, Lagrange. And he was discovered, he was a very young child prodigy, and at age 19 he was discovered by Euler. And Euler realized that his version of calculus of variations is much weaker than Lagrange, this young Lagrange. And so this first theory is due to Euler and Lagrange. Okay? And we profited here in Germany from that. Most people don't tell this story because it's, so you know Euler was forced out, was professor in Berlin, and he had some big fights with the Kaiser, and he left Berlin. I don't know the details of those fights, but as Euler being Swiss, it's probably related to money. So I'm joking probably, but I've told you, some of you know my stories. I have a very good friend who was negotiating with me. I was negotiating, we were with some minister of science, and I was the chairman, and he was a professor from Switzerland, and we were negotiating his salary with the minister. And his name is Italian because he's from Ticino. You know, there's the region in Switzerland, there's one region in Switzerland which is Swiss, which is Italian. It's called Ticino. And the minister said to him, I noticed that you're from Ticino, and then you must be more or less of Italian background and so on. And he said, my friend said, in this negotiation, I am Swiss. So, I don't know, I had some problems. So you know he went to, you know the background, he went to, what was it called, St. Peter, it's called St. Petersburg there, to what is it, Leningrad and now St. Petersburg. And he suggested that the Kaiser, or whoever was the director of the Academy in St. Petersburg, in Berlin, hire Lagrange. So Lagrange came to Germany for a long time before he went to France. You can look up exactly the details, I've forgotten. But, and Euler realized that this young Lagrange had a very good theory of calculus of variations. And I think, if I recall correctly, I think this gives you an idea. Euler gave a very famous lecture in something like that, where he explained what you should do in calculus of variations. This is a long time ago. Okay? So, this is an old subject. I'm sure it was not made precise until the 20th century, but the general idea was absolutely correct. So this is the theory of Euler and Lagrange, very early, far earlier than Riemann, as you see, and far earlier than Levi-Civita. And it's the calculus of variations in order to find the critical point of a functional on curves, which is defined by a Lagrange. Okay? So if you want to think of it, think of that being Lagrange and that being Euler. It's Euler-Lagrange. Okay, so the idea, which you can read anywhere, is this. You just look at this. Phi of gamma plus h minus phi of h. I told you we want to differentiate this thing, right? And now, maybe I'm thinking divided by h, but I'm not going to do it. So what is h? Yeah? So you know, that's a number if you're doing differentiating functions, but here, here is the curve gamma, and then you want to deform this curve gamma, and here we're going into what Maria is acting. Even though maybe I'm going to use arc length later on for this discussion, here, right now, I'm going to deform it by adding something to it, and who the heck knows what I added? I'm just adding any curve to it. Okay? So any smooth curve, so that here is gamma plus h. Now I want to, is somebody call it? I want to add anything. So what about h? H, I think h, we need to assume that h of a equals h of b equals 0. Right? So we want this to be, we want to add 0 here. Okay, so I'm in a coordinate patch, I know what that means. And I just add 0 at the curve, so that's what I do. Okay. So let's calculate it out. So this is where, by the way, I'm going to assume. Let's assume that this t is not here. It'll never play a role in our case. So let's assume it's not even here. So phi of gamma plus h minus phi of gamma equals integral from t1 to t0 of phi of x plus h x dot plus h dot. Okay, minus L inside the integral here of x dot dt. Okay, and okay, that's good. And now we write it very slow. Let's write it very slowly over here. I'm going to make a mistake. Where did he go? He's a physicist, so he needs to correct it. He did. Give me back. He's going to the toilet. He can't stand it, so he has to go to the toilet. So L, let's write the Taylor series, L of x plus h, x dot plus h dot equals, okay, you have to help me here writing a Taylor series. Okay. So, here we go. Partial derivative of L with respect to x, of x dot times h, plus partial derivative of L with respect to x dot times h dot, plus order 2. I'm assuming here L is relatively smooth. In our case, it's really about the smoothest thing you can think of. So I'm not worrying about delicate estimations of order 1 or small O or big O or whatever. This will play no role at all.
Don't you make times x hat squared?
Did I make some mistake?
I don't know. In the Taylor series, right?
That's a Taylor series.
Yeah, so you have L of x and x point, and then
Well, let me put it here. I think maybe I just didn't do it completely enough. X dot times h dot plus O2.
Did you make an H dot there?
Hmm?
Just be the H, no?
I can't hear you, you know.
Oh, is that in the second? Yeah, that's fine.
So this is a Taylor series.
Yeah.
Don't forget, if you don't mind, this is a horrible Arnold Taylor series because, right? Because this is a vector perturbation, and this is a vector derivative. This is the vector derivative. This is the vector derivative. You got it? You can think in one variable. It doesn't hurt, but right. This is the differential of L evaluated at this deformation, right? Okay. Okay. And now, this term is very good. This is a good term because we will divide by h. Remember, I told you what we're doing. We make a deformation with h, right? Subtract off the function, divide by h, take the derivative. Yeah?
What does that even mean? I mean, formally you can do it, but h is a curve, right?
Formally you can do it, yeah.
Formally you can do a lot of things.
Yes, but I won't do it yet. So he's asking the question formally, Arnold would just do this, but he would know it's correct. You're right, I can't divide by a vector, so it's a vector. H is a vector value perturbation, right? And so is h dot. But in fact, you agree that basically what we want to do, we want to make h small and take some sort of limit, right? And h point, I don't know what it is. I mean, how to make it, what's going on. That's all I mean by that statement. I'm glad you asked, but right now that's just nonsense. Okay? And now, let's see here. And what happens, integral from t0 to t1 of dl dx dot, that's that variable, not the derivative of function, that's that variable on x dot of h dot, that appears in this integral, dt. And now our students in Applied Calculus 1 would be very happy, except these are all vector valued, but it doesn't matter, because what you want to do, if you see something like that, is integrate by parts, right? This is what you want to do. You want to kill the derivative on h and pay the price It's capitalistic. You kill the derivative on h and pay the price by differentiating thing. And so you will check me. I hope this is true. This is equal to this thing. So you came back because you knew I was doing something non-trivial now, and you missed all the trivial stuff. But he asked what did it mean to divide by a vector? So this is a good question. Yeah, integrating by parts, and dt L x dot of h, right? That gives this term, except I have to minus off this term. Please check me, I'm going to make a mistake here, as you know. What that gives that term, and what I have to subtract off is this term, right? I hope I did it right. X dot let's check if I did that right. I think I did it right. Right? Isn't that how to do that? That's called integration by parts.
What about dt?
Huh?
dt? Like the dt at the end?
Yeah, I didn't bother writing the dt if you don't
But it's
mind.
there, right?
It's there. Yeah. I'm integrating always with respect to t. Yeah, so I'm integrating by parts. Okay. This is nothing mysterious, right? And so then this is exact. That's maybe what Marie is acting. This is an exact differential. It's maybe I'll put this here, dt. All right, this is exact, all right? And so this is equal to this intermediate term. H evaluated from t0 to t, 1, minus the same thing. You agree? So that's the usual thing you do in applied calculus 1. Except here everything's a vector if you do that. Okay? But this perturbation, I drew you a picture of it over there. Not of Italy, but this perturbation here. Is that our perturbation by h is 0 at the boundary points. Right? So this evaluation at the boundary point, h is 0. Yeah? So that is a beautiful application of integration by parts. Because you will easily check that the order 2 terms that appear here someplace, where's the order 2 stuff? Is it anywhere? Oh, there it is. Play no role in this critical point business, as usual. Play no role. So this integration by part, it says that x is critical for E, if and only if the integral from 0 to t, now I have to put everything in, that minus that, so the first order stuff vanishes. So let me write it in. H, the first term I get up there is still there, dx point. And the second stuff I brought into a good situation with integration by parts. So let's write it. dl point of x and x point times h dt. This So it's critical for E if and only if
Equals to 0.
hmm?
This is 0.
Well, not with H. Yeah. But for example, let's put here norm H, some sort of norm of H goes to 0 for all H. Yeah. And now I'm not dividing by, I'm just saying this has to be small. And so what does that say here? You've got H involved here, right? So, but that says that H is free for me to choose. And now choose H to be any cutoff function. So, which is 1 at a certain interval and then down to 0. You see? Yeah. And so you see what this implies is, of course, that the integral, that what you have inside has to be 0. A cutoff function. Well, it's a cutoff vector value function. So this is ddt. Okay? You get the point? So, something is critical, yes, if up to order 2 terms that you can forget, its derivative is 0. Here, its derivative is this terrible integral, except we have to take this limit. The derivative will be more something like this. This is a vector derivative, right? The derivative has to be 0 for any H. You get any nearby perturbation, it has to be, this is called the calculus of variations. We're taking the curve, and we're looking at all perturbations of the curve, and it's saying that the derivative for all perturbations of the curve has to be 0. Right? So I can choose H, or you can choose H. So what we do is we choose H to be 1 here and go down to 0 here where it doesn't count, right? And so we just get this thing, and the only way for that to go to 0 is what it is. Okay? Yes?
Wait, so first you are writing the Taylor expansion, and then you're calculating the interval of one of the terms in the Taylor expansion. And how does that relate to x being the critical point for E?
Well, I didn't get any of this, so it's too fast for me. So
I don't understand why, well, doing all that Taylor expansion and everything, how does that relate to x being critical for E?
okay. I have to define what it means to ask something to be critical
Yes.
for E. And I say that something is critical for E if it's the derivative vanishes. Okay? That's the definition of critical point. I have to define in some way what is the derivative. This is one reason the analysis on infinite dimension, this is infinite dimensional space here, that's one of the problems, right? We're moving H in some infinite dimensional space, right? So one of the definitions would be exactly what I just wrote down on the board. For all H, this derivative vanishes, and when we divide, he asked me to dividing by a vector, but just divide by the length of H. Okay? Okay. So that limit has to vanish for all H. And now H is in my hands. Right? H is in my hands. I can take any perturbation of the curve into the space of all curves, which is a terrible space. But I take cutoff curves, if you like. I mean, which you can see what I mean. Just some sort of cutoff thing, and show that in fact the only way that can happen is if this generalized derivative goes to 0, which you rightfully asked about, for all H, means that in fact what I have inside has to be 0. Okay? You can easily check it, and I checked just now in my office what's in Arnold, and he makes this argument very precise, but that's exactly what he does. He takes cut off and so on. Okay, it's the usual thing. Well, that is a very, 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 very beautiful thing. This equation here is a differential equation. Yes? It is written as one equation in the notation of Arnaud, but it is n equations where n is the dimension of the manifold, right? Because this is a vector value thing, this is a vector value thing, this is a vector value. So this thing here is the Euler-Lagrange equation. And it's an ordinary differential equation. It's the second order ODE. Okay. And so for L equal the square of the norm, and you see here, I made these definitions. My H is some terrible thing. Arc length, I don't know anything. Yeah.
But L is a function that takes values in R?
That's right. Because I did, yes. Well, let's look at what it, I mean, in our case, yes. It's a priori any reasonable function, say smooth or something, real valued function. A priori. Of course, that's unrealistic. There will be some positivity conditions and so on, but I didn't use anything here. Right? And in our case, L is the metric norm squared. Okay? Just so you, L of x dot, let me write it down so that you know I can write it down. I'll prove to you can I write it down. All right? Well, it's the quadratic form, Gij. Okay, am I allowed to write it downstairs? I think I'm allowed to write it downstairs. Now, the quadratic form depends on the base point, right? Because x is in the manifold, right? And now we're measuring tangent vectors, and now here we go, I'm okay. Right? That's what it is. Right? So it's the norm of the derivative. It's not very, so in our case, it's really incredibly simple. Okay? Okay. Good. So, then somebody was smart enough to look and think, and that person is probably somebody like Levi-Civita, because this whole business existed before we understood the notion of connection. Okay? And that's what Deepak or Deepak, how do you pronounce it? Not D. In your language you have the, what kind of sounds do you have, like e? You know the English word deep, is it the same E as in
D, yeah, D.
D, it's in D.
Yeah.
Okay. He mentioned that I forgot a key point, so if you take nabla, okay, to be the Levi-Civita connection, symmetric metric connection of G, then the connection ODE and the Euler-Lagrange ODE are identical. So you knew you did something very, very right, very correct in this calculus of variations. Yeah. You recall what I mean. This morning I reminded you what the connection ODE is. You talk about parallel transport and it's parallel, the curve is parallel, and so on. It's the same, it's identically, it says that you write down the structure constants and they are exactly the Christoffel symbols of this situation. So it means that you can, because the differential equation here obviously involves derivatives of the metric, right? Because you differentiate around it here. So it says that the Christoffel symbols are expressible as derivatives of the metric. I could write them down maybe, but I make a mistake. Okay? You probably, you've seen this. The Christoffel symbols can be written in terms of the metric. And so that's a wonderful thing, and it's maybe not surprising. It says that we have the right notion on both sides of the equation. But the interesting thing is Levi-Civita and his whole idea of connection, Riemann and so on. This is more or less 1900 Christoffel symbol. And Euler-Lagrange is in the 18th century. So there's a tremendous development of time before people understood something. Okay, and here's a fact. Let's call this dagger. And it uses dagger. Yeah.
So, does this mean that only for the Levi-Civita connection do we have that that a curve parallel to itself is a 3D set?
Say it again.
Only in the case where we have
the metric connection, which is symmetric, Levi-Civita connection, yeah.
where the curve is parallel to itself becomes exactly the geodesic.
Yeah, because you have to have something that's related to the metric in a strong way. So I see what you're saying. There might be some other connection that's related to the metric in some other strong way that still does the job. I think the answer is no. I think this is forced on us. And it's interesting you asked that, because in the pseudo-Riemannian case, I mean, you have the connection and so on. I mean, right, you don't need to think about this metric. So in some sense, you want to think here, which is correct for you, I think, in my opinion. And you would like to know what is the way to avoid going here. Right, because you start talking about length and you get outside the light cone and so on, I don't know what's going on. I mean, it's a very mysterious thing, right? I don't know, your physics people understand this probably very well. I don't. Here is a fact that uses this that I'm going to, so this is second order ODE. Where did I write this? All right? And this is then a first order ODE. On the tangent bundle. Right? The thing I talked about this morning. You take, it's the usual way. Yeah. The geodesic flow, either to minimize the integral by the Euler-Lagrange equation, or to have parallel transport of the curve equal itself, this geodesic flow is a first order ODE on the tangent bundle. Okay? Okay? As I said and screamed at you this morning, there's a local one parameter group action. Right? Yeah. So there's a fact that's a calculation here, is that the norm square G is invariant by the local group action.
Who is the group that's acting? Oh,
I'm gonna get mad, I really like Maria, but I'm gonna get mad, not at Maria, but at the terrible didactics in mathematics, and my friend came on, it's not his fault, is an ODE is, a first order ODE is a local one parameter group action. That, it is that. You can write it down with derivatives and blah, 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 but it is a local one parameter group action of diffeomorphisms, punkt. I don't know how to say punkt in English. Period. Okay? Please. Okay? And please think of it this way. Here's the manifold. Yeah? And here's the time axis. And if you have a point in the manifold, you can integrate the differential equation with the local action for a certain time. You know that. For a certain time, you can integrate any differential equation. This time length that you have, where you can integrate this thing, depends on the point in the manifold. So if you have another point, maybe it's a smaller time interval. Then you have another point, maybe it's another time interval. Maybe sometimes it's the global time interval. The domain of definition of the one parameter group action is this open set. Okay? One parameter group action means G of T plus S is equal to G of T composed of G of S. Excuse me. Yes, that's all there is to it. Wherever it's defined, wherever it makes sense. Because you might integrate here out to something, and then you might integrate here too far, and so on, and so on. Yes, you go to some point in the manifold, you don't have much more time. Okay? So when I say that you have an ODE, first order ODE, it's associated with one parameter group, local. Something is invariant, it means it's invariant. It means I take the orbit and the function stays constant on it. Okay? Or the level of the vector field. The vector field kills the function you're discussing. It's constant. Now, this is an easy thing that you can compute, but it must be obvious. It must be obvious that this norm is invariant by the action that defines geodesics. Right? I mean, it must be somehow obvious. And I do not know a direct proof. I only know this proof by calculation. I want to think of a better proof before I lecture. I know that this can be proved conceptually. I will show you now and later this afternoon that this is conceptually obvious. But I don't know a direct proof of that fact. Strange. Okay? Now, that was the Lagrangian point of view toward geodesics. And the fact that these two differential equations are the same says the Lagrangian point of view and the Levi-Civita point of view is the same, remarkably enough. And Levi-Civita is good for indefinite metrics and so on, so somehow Levi-Civita is better, right? Let me start the second part of this. point of view. Let me write, I'll let my physics friends make fun of me to tell me how stupid I am. I'll give you all physics people a chance to figure out how stupid I am. Momentum that's a physics word. I'll gamble on it. I worry about the numbers because every physicist has really precise numbers in his head about what is what. Am I close? M is mass, V is velocity. Do I need a constant in front of this? A half or something? That's okay?
Yes.
Got it? You agree?
So much space between equal and n.
Yeah, I left the space here for a constant. Okay? Momentum is equal to mass times velocity. It makes sense, right? If a huge train is going at some velocity, right, and hits a wall, and it goes at the same velocity I am, I mean, you know, I'm huge, but the train is huger, and there's more momentum, and so on. It's mass times velocity. Then, as a mathematician, you look at that equation, and you say that's interesting. Velocity in a manifold goes in various directions. Right? We're talking about velocity vectors along a curve. Right? So maybe this mass, maybe this is a linear function of velocity. By the way, another physics word for momentum, by the way, in German is impulse. Right? It's the same word. Right? Impulse? Same. In German it's impulse. Right? You don't like this word? You don't know this word?
That's like
I-M-P-U-S. Huh?
something else included.
What?
In the German word.
But it's the same at the moment. Yeah, okay.
Up to some constant, I'm sure it's the same thing. Mathematician, if you don't regard this thing as being important, you've lost a huge amount of deep thinking by serious colleagues in physics. Well, that's interesting. By the way, the standard letter for momentum is P. Do you agree? Get used to it, mathematicians. The standard letter for momentum is P. Momentum is a linear function, so P is a linear function of velocity. So this means if I go from velocity in the tangent bundle, whatever that means, I should go to momentum in the cotangent bundle. Right? Because fiber-wise, a velocity vector in one fiber is associated, maybe if I write m times v, a linear function. So Newton and probably Archimedes probably knew that momentum equals mv. I mean, there must be a way of Galileo for sure. I mean, these people really knew about momentum. Momentum is a linear function of velocity. So we should understand how to go from a linear function of velocity to momentum. Well, the word you want to put here is Lagrange. Because we had the Lagrangian and talk about a Lagrangian theory and all of this stuff here. And the word, famous name you want to put here is Hamilton. Now, mathematicians have heard of the name of Hamilton, but probably only because he discovered, that people say he discovered the quaternions. That is more or less trivial discovery in my mind. Psychologically, it's maybe not trivial, but mathematically, it's a trivial. So you know the quaternions are some trivial thing. And there's a long search for such a division algebra and so on, but that is not Hamilton's main contribution. He did a lot. And what I'm talking about here is really fundamental, in my mind, far more fundamental than any little quantum. So we have what we call here Lagrangian mechanics. And what we have here is Hamiltonian mechanics. So Lagrangian mechanics and Hamiltonian mechanics. And it's the same. And the Hamiltonian viewpoint is, in my opinion, very much more powerful. So this connection here, in the sense of how to go from one place to another, is called the Legendre transformation. I don't know the history well enough, but he had very close contact with Lagrange. And you will see in this, I will talk about the Legendre transformation in a minute, well, next lecture. But you will see that it's the beginning of Lagrange multipliers. You know this method of Lagrange multipliers for finding critical points, functions restricted to certain subnet. So this Legendre transform takes this thing from the tangent bundle to the cotangent bundle. And then we will see that the key fact that you will see in the next thing, fact that we will use, is that the cotangent bundle has canonical symplectic structure. Whatever that means, there is a canonical thing going on here that we can use that will tell us a great deal about the geometry of geodesics. Okay? Let's stop here, make a break of, how long should we break? What do you like? 10 minutes, 15 minutes? Would, is 15 afterwards too much of a break?
The standard is usually 15.
You're not exhausted by me? Well, how about 10, take a 10-minute break? 10 after. Okay? Right, thanks.